Yay!
Yay! All right, next object. We did a rod before, so now let's do a ring or a hoop. So this thing now has, let me go ahead and get, because that looks like maybe there's something in the middle. So here is something where all the mass is on the outside, and it's got a radius of big R, right? So what is the moment of inertia of this thing as it spins about the center? So this thing is just spinning about its center in that way. So what is the moment of inertia going to be? Well, the moment of inertia is just the sum of mr squared. So what are we going to do? If you chop this thing up into lots of little dm's, right? This is actually really easy because how far away are all those dm's away from the center? They're all the same distance r away. So all you have to do is just add up all the little dm's. And so this is just going to be mr squared. I mean, there's just nothing to it. All the mass is, whoops, I don't like that box. All the mass is the same distance away from the center. So we're sort of done. So all the mass is that distance away from the center. There you go. So the moment of inertia of a ring or a hoop is just mr squared. Well, that was too easy. Let's do something a little bit cooler. What about something related to that? What about a disk, a solid disk? So, okay, so now let's say we have another thing like this. Now let's leave that sort of looking like it's filled in a little bit. So let's say that this has, the whole thing has a mass of m. It's still got, let's say, a radius r. So how are we going to figure this out? Well, since we've already done the ring, let's see if we can be clever. What do we add together? Maybe we can add together a whole bunch of little masses to sweep out the disk. And maybe a clever thing to do is to add up, since we've already done the rings, let's add up a whole bunch of little rings from the center all the way out to the edge. Each little ring has a radius r, little r, right? So sum up thin rings from 0 out to r. That might do it. So once again, we start with this. We say I is dm r squared. I know that I'm going to try to integrate from 0 to r, right? But I need, once again, I need to change variables from dm to r. And then I should have it. I'm sweeping out these rings all the way from 0 to r, so I'm sort of sweeping out the area of the disk. So how do I change variables? What I'm going to do is kind of the same trick that we used before. So let's write it down sort of in words first. So a little bit of mass compared to the whole mass for the disk, if it's uniformly distributed. We're talking about rings, right? So this should be the same. What's a little mass? It's the ring. So a little bit of mass compared to the whole mass is like the area of a ring compared with the area of the whole disk. That's going to be the strategy. So let's write down, what's the area of a thin little ring? Well, if it's infinitesimally thin, it turns out the area of the ring is just going to be the circumference times its thickness. We can get away with that. So it's going to be 2 pi times little r. That's the circumference of each of these little rings. And then its thickness is dr. There we go. And what's the area of the disk? Well, that's easy. That's just pi times big R squared. Neat. So the pi's cancel out. And now I can solve for dm and plug it right back in there. And then we're all set, because now I've rewritten it in terms of r. So this is going to be 0 to r. What is my dm? Now it's going to be move the big M to the other side. 2 times big M over r squared. And what else do I have? I got a dr. I got an r squared and then another little r, so I have like r cubed. Right? I think I got everything in there now. So 2m over r squared dr r cubed. Okay, cool. Well, the big M, the big R, those don't change. So that's just, and the 2, those are just coming out front. So the integral of r cubed dr, that's pretty easy. That's just r to the 4th over 4. All right, so this is just going to be 2m over r squared. And this is going to be r to the 4th over 4 from 0 to r. I mean, the 2 and the 4 are going to cancel for sure. So when I put in 0, I get nothing. So r to the 4th, when I put in big R, that 2 of those cancel from the r squared in the denominator. So you probably already see what you get. 1/2 mr squared. Neat. There we go. So the moment of inertia of a ring or a hoop was super easy, just mr squared. The moment of inertia of a disk, we got that by cleverly integrating rings. Since we had just done it, we might as well use it. Rings all the way from 0 out to r to sweep out the disk. And what you get is that it's interesting that it turns out to be half. The moment of inertia is half of a ring or a hoop of the equivalent mass. That's kind of neat. It makes sense though, right? Physically, because if you go from a ring or a hoop of mass m to a disk of mass m, what you're really doing is spreading that mass out and moving some of that mass closer to the center. So if it's moving closer to the center, it should be a little easier to spin. So that kind of makes sense. It's interesting that it turns out to be exactly a half. That's not obvious, but it should be less than the moment of inertia of a full ring or hoop. Okay, so on to more objects next time.